Hello everyone, Extreme Tipper 7 here. So, Space Engine is full of quintillions of planets. That's one with at least 14 zeros after it. But essentially what I discovered was a very, very fun planet. It's a procedurally generated one, which is what that RS8513217325 or whatever says up there. So I decided to rename it. This is essentially a planet that's right at the edge of the Milky Way, interestingly enough, and it could be real, it could not be real, but the conditions are right based on the generation algorithms that say, okay, wherever this planet is, it's able to exist. And the reason why I highlighted that is because what we're looking at right now is the edge of the Milky Way galaxy. We are technically still in the Milky Way galaxy, but also outside of the Milky Way galaxy. In the way that if you're looking at a cloud, you're near the cloud, but you're also really far away from the cloud, but you can still see the cloud. So let's see here. Every bit of these dots is probably going to be another galaxy at this brightness and distance because we're really, really far away from the galaxy's, starry zone? I don't know. There's more astronomical terms for this, but I think it's more fun to speak like this when I know the astronomical terms, but I just can't pull them off the top of my head. Because how would a regular person just be able to describe all of these things? But that's the main thing. Right now, we're at a place that has a binary star system on a sand planet. It's not really sand planet, but what it can be considered is a very deserty planet. And at the same time, even though it's a desert, this planet is really, really cold. That's why I called it Sand Siberia, because it's basically cold Tatooine. Gasp! I said the word! Oh no! Disney's gonna be so angry. So that's why I called it Sand Siberia instead of Sand Tunisia, because Sand Tunisia is already regular Tunisia. So instead, it's Sand Siberia. Now, I don't know exactly why I lingered here so much, but that's probably so that I could give myself plenty of time for narration, which is what I'm doing right now. So, in general, what I like to do in Space Engine is I like to find areas that I can spend a lot of time in just observing how things change, because that date down there at the bottom is able to be adjusted to be real time, and also to be fast forwarded. So this video was recorded on March 4th. I used the real-time button, and that was one of the markers that essentially gave me the ability to say, oh, this is one of those early March videos. Alright, so that's going to be part 1. Next up, we're going to be dealing with an increase of stellar magnitudes so that you can actually see more objects in the sky. Which means that everything that you see is more than likely not going to be just a star, but is going to actually be a galaxy or nebula. So, let's take a quick peek around and see what I remember. So that's a star from our local area. Oh, it has 5 planets. That's another star. Interesting. There's still a lot of stars, but they're also very blue. That's the other thing. A lot of these stars are going to be blue. That's what I noticed right away when increasing their magnitude. A blue supergiant is a really, really bright star. And this is one of the things that I was showing here, because it's not exactly apparent why all these stars are blue unless you've gone to... oh dear. What is the... first through 5th grade? Are you smarter than a 5th grader? My goodness, I hope you're smarter than a 5th grader. But that's the thing, that title should probably be updated to, do you have the localized knowledge of a current 5th grader? It's a mouthful, but the reason for that is because 5th grade knowledge changes every 10 years. Are you going to be keeping up every 10 years with 5th grade knowledge? That's why that show is rather interesting to me. Because a 5th grader of today knows more than anybody in terms of how the galaxy works, how the planets work, how gravity works, how lightning works, than people of 500 years ago. So that show really was an interesting, let's call it social experiment, to see how people reacted to the, oh my goodness. But it's just, if you say that you're going to school, and then once school is over, you never learn again, that's what that program is also about. Oh no, I'm missing narration. We're at the nebula that I love. This is one of the brightest nebula that we have, and I'm just kind of slowly rotating the nebula. I was just filling time until I got to the nebula, because I have to basically have a reason to just sit around here and watch the universe, because there's not really too much interesting, unless you count the restaurant at the edge of the galaxy, but that's not at the edge of the universe, that's just at the edge of the galaxy. Oh yeah, you better believe I'm gonna make Hitchhiker's references. So that marker right there is the let's see here, is it the Carinae Nebula? The Carina Nebula. And the other thing is, there's another planet that I started with that's from a different point in the Milky Way galaxy, which I called Frosnia, which is a frozen Bosnia. And the reason for that is because its average surface temperature is negative 169 degrees Celsius. That's pretty cold. I don't have it in Fahrenheit because I'm in Space Engine, and Space Engine loves to be more precise than Fahrenheit. Got him. So, Frosnia, I'll show Frosnia as well. But Frosnia is, let's see here. It says here, cold, airless, mini aquarium with life. Which means that it has ice, and it has life underneath that ice. So that's one of the interesting reasons why I chose that specific planet. I really gave myself a lot of room for narration, which is nice. Thank you, Past Me. Alright, so let's see here. We're going to, right now, speed up the time itself. Technically. That's what the time scale button is doing. So we're going to rotate, and I'm going to try to follow the galaxy as much as I possibly can. But the other thing about this is that this is a view that people don't typically get, and will never get if they're human unless they go to this specific spot and look at this specific configuration for this specific planet. And also, it depends on the version of Space Engine you're in. This is one of the latest versions of Space Engine, which means that it has a lot more features, and it's got, just in general, a bunch of different other things. But, slowing down. So, it's gonna be really, really, really dark out here until the suns come up. So, we're going to be seeing the exact reason why I also really, really like this planet is because it's a dark world, and you can see so many stars and so many galaxies because there's not even localized starlight pollution. So that's the other thing that a lot of people don't think about is light pollution on the ground is bad, but once you're in space, inside of the galaxy, there's still a lot of light that's just kind of hanging around out there. You just can't really find it that much. And resetting back to real time is one of the ways that I can say that it's going to take... Oh, I got a whole month before this galaxy rotates enough to that it points that it's, oh my gosh, 90 degrees? Yeah, 90 degrees compared to its horizontal aligning with its galactic ecliptic. So that is, let's see here, April 19th? So around April 19th, I'm probably going to come back to Siberia and look at it from Frosnia's perspective and see where Siberia is from Frosnia's perspective. But right there is April 20th. Didn't do that on purpose, but it just so happened that that's where you can see the red shift of the galaxy as well as the light being bent from the localized atmosphere of the planet that we're on. We really do have an atmosphere on this planet. It's not breathable to humans mostly. It's methane, I believe. It's a lot of methane. It's cold methane. Which kind of makes me wonder, what is the temperature at which methane can be liquid? And that's something that I don't have off the top of my head because I'm not that much of a nerd. Some people are that much of a nerd, though, but I'm not that much of a nerd. Alright, so, it's... oh my gosh, date. Please, 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 please. There. Ah! April 15th. So let's see here. April 21st. That is not what I intended at all. So I must have misaligned. So what happened here is I probably just entered the wrong digit. Because it looks like it's March 4th still. And I was trying to get the time frame right. So I said, how much is it between what we are now? But I just kept experimenting and seeing, what did I do wrong? Because I'm pretty sure that I got to the 21 hours, and I'm just like, no. I seriously caught the exact point of red twilight, the red flash of this planet. But I also found out this is when sunrise is. Sunrise is going to be something that I can track. 22 hours. And what is that? 51 minutes? So 10:51. On March 4th at 10:51, that's when the sunset is. And it's going to be 10:51 for a bit because these things still do orbit. And when they get to their maximum zenith and maximum azimuth, it's going to be different. Right now, it's been about 10 days since I made this recording, so not much has changed in terms of the galactic neighborhood, but in general, I'd say that it's going to be something that we can really just take our time with, because space may be fast, but space is also very, very slow. So this is going to be another wonderful experience that's an alien sunset. So here we have March 4th at 9:54 p.m. Central Standard Time. Well, it's their standard time. Essentially, I forgot what time it was local to me, but I'm gonna make that time the Central Standard Time since my time zone. So I had to factor in how many hours difference I was from this clock. And, oh dear. No, that's going in the background. That's staying in. I'm doing this completely raw. It's going to be both raw and edited. I'm not going to cut out any mistakes. It's just going to be me experiencing it and narrating what the heck is with this video. There's not a lot of guides in these types of things because Space Engine is a game that isn't a game. It's a simulator that's not really a simulator, but it's also partially a simulator. It can simulate an entire galaxy. It can simulate an entire solar system. It can simulate an entire universe. But what you do in that universe is completely up to you. You can just look at things. You can just look for things, as in, I wonder what the localized constellations in the area are. It can be, oh, I see. So that's what that looks like from that angle. And since it's really from Earth's perspective, if you start from Earth anyway, you'll be able to have the constellations. Oh my gosh, what is that hypergiant doing over there? Oh my gosh, poor hot Jupiter. Alright, so we're gonna just fast zoom over here real quick. And this is one of the things. This is the type of planet that is just kind of stuck in limbo. It's got a surface that can melt most metals. 1200 degrees Celsius. So you can probably tell why this planet's a little bit orange. Let's see here. Where are we headed? Oh, also the thing with the cursor, I don't know what that is. I didn't have that in my native rendering, so I'll have to look into that. If it's not too distracting, it won't matter too much, but it does kind of look like the old school error type things. So, here is the tiny moon next to the giant object. So that thing is clearly glowing because of how hot it is, but this thing is also very hot. We went from very, very cold to very, very hot. Oh, it has a glowy effects. I forgot about those. So when something gets hot enough, it can start to make, you know, like the same effect that, oh my gosh, what do you call the thingy with the sun where it does... It's not chromatic aberration. It's... Oh well, I'll think of it later. Either way, I was trying to get a nice angle so that I can show how big these things are and how small they are. And then I just remembered, actually, I can just do this thingy. There's an entire tool to where you can set the scale of things, you can set where things line up, you can set what things line up. And so I just started playing around with this thing a little bit. But it's always surprising when there's life in the random systems that I select. Because it means that the conditions, I was about to say coordinates, the conditions are right for the habitable zone to be exactly where that planet is, so might as well say, hey, there could be life there. It just depends on the temperature and the type of life. Because it doesn't matter if it breathes methane, if it's alive and it breathes methane, it's still life that breathes methane. But that would mean that if it breathes methane, it would exhale something other than carbon dioxide or oxygen. That's the key factor that we don't typically think about most of the time, is that we're carbon dioxide exhalers. But for creatures that breathe carbon dioxide, they are not going to exhale carbon dioxide. Plants exhale something other than carbon dioxide. So I consider us like sort of like miniaturized reverse plants in a way, but we don't photosynthesize. We burn. It would be interesting to think of what a plant that sunburned would look like, because if we were more like plants, we wouldn't sunburn. We'd be able to literally feed off of the solar energy itself. I forgot how many objects were actually in this system, but there's a lot. And there's gonna be some that are gonna be more interesting than others. But I don't get to make that decision. You do. So let's see here. 1, 2, 3. There we go. So, the sizes of the planets and or moons and or asteroids are all displayed down below. So, the biggest one right here, the reason why I selected that orange glowy is because that's an Earth-sized orange glowy. 13,000 kilometers at the equator, which is, Earth is about 12,000 kilometers. So it's about 1,000 kilometers. Ooh, thicker. Little bit thick, boy. But it goes all the way down to... Let's see here. 6,000, I think, is... 6,000 is the smallest planetoid before it starts being a little bit not round. But San Siberia here, the one that we were just on, that's 14,000 kilometers, which is at least 2,000 kilometers larger than Earth. And then we get down to this one, which is 9,000 kilometers, which is just slightly smaller than Earth. But it's big enough that it has clouds, an atmosphere, and a specific gravity. Oh dear, I used a sciencey again. It has a gravitational pull of... let's see here. I can't see what that says right now. I think... Nope. I cannot see unless I individually inspect the planet like that. However, there's a bunch of nerds that will be able to tell you what a specific gravity is based on all those other numbers up there that I don't know. But I'm not that type of specific nerd. I could be, though, but I'm not right now. But San Siberia is one of my favorites because I was just exploring and I found a planet that was Earth-sized, Tatooine-like, cold, and it's just, that would be really interesting if we figured out a way to just make it so that we can terraform, well, not terraform, I mean, at this point, we need to be able to do planet form at this point. If we can planet form negative 160, then that just means that no planet that cold is ever going to be a problem. Which is why, if Siberia is able to go down to negative whatever Siberia goes down to, and we still survive in regular Siberia, this is going to be a cakewalk. Now, let's see here. What is the smallest? We're down to the 2.8K now, so these are getting to around the size of our regular moon. That one is almost able to be confused for our moon. That one is way bigger than our moon. So I kind of just, to set the scale, I move the distance, and if I want to show the scale of how big a certain thing is compared to a certain thing, I don't zoom out. And once you see that green marker right there, that means you're getting close to being able to have an atmosphere in life, but you may not necessarily meet the conditions for it. Which is why these planets keep getting greener and greener in terms of their numbers. And this is the first planet that we have that has Aurora Borealis on it. Which is to say, a magnetosphere. A magnetosphere is just what other people would call a magnetic field. But that's the super duper sciencey name for it. In order to have aurora, you need to have a magnetic field to repel solar radiation. Or stellar radiation if you're not here in this solar system, because it's stellar other places, I guess. I don't know. Science disagrees on whether or not we have to call other places stellar systems solar systems still, because it's our reference. It's like that us versus everybody thing. Either way, let's see here. This one's 9.6 kilometers. This is the second one, and then San Siberia is the next one over. So San Siberia does meet the conditions for life. Because if anybody can exist in regular Siberia, San Siberia can exist too. It's just the methane is probably going to be the problem. So we have environmental suits, or we convert the entire atmosphere to oxygen, nitrogen, helium, argon, xenon, and other trace chemicals. Oh, yeah, that's the other thing, too. San Siberia has polar ice caps. Which is nice, because it seems like polar ice caps are kind of required for a regulated planet. Which I don't know why. I guess hurricanes do the thing where they bring the cold. And you'll notice that There's quite a few hurricanes along the equator of San Siberia. That's not a coincidence. That's based on a whole bunch of parameters for the procedural generation. I told you there are a lot of objects in here, and I don't even remember how many there are, but there's at least 50, I think. That one kind of looks like Venus, which is why I stopped on it. It's smaller than Venus, though, so I figure it just had an atmosphere that made it really, really toxic anyway. But once you start getting down into the smaller sizes for things, they just start to become more and more moon-like. And eventually, you'll just only be able to have asteroids. But this is the localized neighborhood of San Siberia. San Siberia has quite a few neighbors. And I also had fun rotating the planets and moons a little bit, because when you're in this view, you can rotate it and orbit it. And I also do a few orbits in Space Engine on my own, too. Also, I'm going to be really sad if I didn't actually push the record button here. There it is. Good, we're good. That's going to stay in there, too. But since I am still recording, that means that I have many more things that I need to get off of my head. There's a lot of craters that you see a crater, and you don't really realize how big a crater is until you actually go in it, and it's the size of mother fricking Australia. Now that's a little bit of a biggie. But this is the other thing I'm doing. Remember how I said about the perspective shift? The nearest object relative to the closest object over fills the screen with how big it is. So this one is 2.8. And from that 2.8, we can see that we have at least maybe about 30% of the surface visible. But once we get back over to this one, oh boy howdy. Boy howdy, we barely have any room at all for it. And that's only 3.5. But that's what happens when you start from a localized scale. Oh, that crater right there. That crater right there is 300 kilometers wide. Nah, it's not that big. It's only about 25. Only 25, you say? 25 kilometers is an entire trip to a gas station. Or a petrol station. Ouch. That's one hell of an aurora you got there, buddy. So, as you can see, we have a little bit of space that we can squeeze in there, but we don't really have the ability to get all of it on screen at the at the scale we started with on the other moons and or tiny planets. But from this view, you can also see a little bit of the surface of the gigantic planet, which is why I chose this view. But, ooh boy. Ooh, volcano. Now that's something too. I'm like, oh, volcano. Fun. And also the planet has rings. This one is the largest life potentialer we have in this system besides San Siberia. It's gonna be warmer than San Siberia though, because I think this one is 400 Celsius, so it's pretty hot. But it's not hot enough that life can't exist on it, because it's not melt your spaceship hot, I guess you could say. There aren't as many clouds on here, though. And that's probably because... Let's see here. Does it have an atmosphere? It looks like it may not have an atmosphere. But it does have enough gravity to be able to... Ooh, I got distracted by playing around with the lighting angle. But it doesn't have any atmosphere, yet it has aurora. So what the heck is going on there? It's gotta have an atmosphere if it has an aurora, unless it just has a magnetosphere without an atmosphere. That will be weird. I mean, it's possible, but I'll have to investigate more. Maybe I don't know, maybe I missed the atmosphere of this planet. It has a ring system, too. And... Nope, it has an atmosphere. I just don't know what it's made of, because it has clouds. I'm glad I rotated the planet enough to be able to notice those clouds at nighttime, because they weren't around at daytime. But it looks like we're getting towards the close of the video again. That was a brief tour of Siberia's localized network. And oh! Yes! It's another galaxy! Right nearby! When I say right nearby, it is currently 600 and something light years away. So that is not a very short distance at all. It's hot, arid Carbonia. This one. 554 degrees Celsius. See, this one just tells you what its atmosphere is. It's got carbon dioxide. I forgot what C2H is, but it tells you there. That's why I'm like, wait, why doesn't this one have an atmosphere? Or maybe it has such a tiny atmosphere that it doesn't really count as an atmosphere. Because this one has a halo, too, for the atmosphere. And there's Siberia in the distance. It's currently 419 astronomical units away. So, when we go back to Siberia, you can see how far away it is from where we just were. But this is our localized system, and Siberia is one that I really find interesting to be in. So, thank you very much for listening to me ramble on for apparently half an hour. I mean, some people can't go for half an hour, but I can. So, thank you for sticking around.